Okay, lecture 55, hypothesis testing for a difference of population proportions. So we've looked at hypothesis testing for a difference of population means. Now we're going to have two different populations, and we're going to look at two different population proportions, one for each population, and we are going to be interested in asking questions about the difference between those population proportions, all right? So all you need to know how to set things up, and you need to know what the test statistic is. Once you have that, you're going to be able to do these kinds of tests. So let me start with background. You got a bulleted list there, so let me just run through these real quick, and you might want to pause me to make sure you get them all written down correctly. So the first bullet, what I have, as I said, we have two separate populations, each divided into two categories, success and failure. There are no connections between members of one population and members of the other, so they're completely separate populations. Success, failure here, the two categories in each. All right. The success category in the first population has proportion P1, we'll call it, and in the second population, we'll call that success, the success category having proportion P sub 2. All right. That's our notation. Our null hypothesis will always be P1 equals P2, or as we usually write it, P2 minus P1 equals 0. So again, we're going to claim in the null hypothesis that the two proportions are equal, which is just another way of saying their difference is 0, right? Okay, we perform N1 independent trials from the first population and N2 independent trials from the second population, and recording the number of successes, X1 and X2, right? So you can see we can set up our sample proportions for each population. And here, we don't have an initial values for P1 or P2 because we're just going to claim that they're equal. We don't claim that they're equal to a certain value. So our way of making sure we have a large enough sample is that we want at least 5 successes and 5 failures in each population, or I should say in each the set of trials we run in one population and the set of trials we run in the other. We want at least 5 successes and 5 failures in each. All right, then we can be pretty assured that the sample in each size will be big enough that the conclusion of the central limit theorem that we essentially have what's going to be z random variables, normal 0, 1, for our test statistic will hold. Okay, so we need that condition. And so we've got a little bit more notation. What is P1 hat, the sample proportion in population 1? It's, of course, X1 over N1, number of successes over sample size. In this other population, the population proportion there, the sample proportion there will be the number of successes in our sample in our N2 trials divided by N2, the number of trials. And now we have something else. We have what we are going to call a pooled proportion. And that's simply if we take the sum of the successes and divide by the sum of the sample sizes. That's P bar. We're going to need that in a minute. And of course, anytime you see a Q, it's 1 minus the corresponding P. So Q bar is 1 minus P bar. Q2 hat is 1 minus P2 hat. Q1 hat is 1 minus P1 hat, of course, right? Okay. Now, what is our test statistic? After you know all that, you basically just need the test statistic. And it is z random variable. And it is, well, okay, I guess I should, we're assuming that, again, the null hypothesis, I'm just going to say null hypothesis is that P2 minus P1 equals 0, right? I said that already. There's our null hypothesis, P2 minus P1 equals 0. So our test statistic is P2 hat minus P1 hat divided by, and it's a little bit more involved, it's that P bar times Q bar over the first sample size plus P bar times Q bar over the second sample size. If our sample sizes are big enough, we can be pretty sure that we have pretty close to a z random variable, a normal 0, 1 random variable there. So that's all you need to know. right? I mean, what is the alternative hypothesis? Of course, it's that this is greater than 0 or less than 0 or not equal to 0, right? So you got all that. You got the test statistic. You can do hypothesis testing now with the difference of population proportions. But let's just run through one example. All right. The marketing director at Yum Yum Snacks, your boss, is convinced that your new treat, chocolate-covered cherry bombs, is preferred by both men and women at the same rate. You, however, suspect that it is more popular with men than with women, and you conduct a survey to decide once and for all. You survey 45 men and find that 32 of them like chocolate-covered cherry bombs. You survey 48 women and find that 21 of them like chocolate-covered cherry bombs. Prepare a short report to deliver to your boss. That's all we have to go on. All right. Well, we see that we have two completely separate populations, men and women, and we're not assuming there's any connection between them, right? There's just a bunch of men here and a bunch of women here. No connection. They're randomly chosen. So we also have success over here for a man is likes chocolate-covered cherry bombs. Failure is doesn't like. Success for a woman, she likes chocolate-covered cherry bombs. Failure is she does not like. All right. So how many successes and failures do we have? All right. Out of the men, for men, which I guess I'm calling that population 1, there were 32 successes and a total of 45 minus 32 is 21 failures. Okay, so that's bigger than or equal to 5. Good to go. Women, which is population 2, there were, was it 21 successes? Yes, 21 successes. And there were a total of 48, minus the 21 would give you 27 failures. So they're both bigger than or equal to 5. So we can go, right? We have what we need. We feel pretty sure that when we calculate our test statistic, it's going to be a z-random variable, and we can go forward. What is the null hypothesis? The null hypothesis is always that the two means, the population means, are the same. So like I said, it's P2 minus P1 is equal to 0. What's the alternative hypothesis? We're testing, excuse me, we're testing that we think it's more popular with men than with women. So we think the mean for women will be lower than the mean for men. The mean for, sorry, not the mean, the proportion for women lower than the proportion for men, so we expect that this will be less than 0. So it's a left-tailed test, right? And you can see now, like I said, it doesn't really matter which one we call population 1 and which one we call population 2. If we turn it around, we would be, you know, if this were women, if this were men and this were women, then it'd be P2 minus P1 greater than 0, and we'd be doing a right-tailed test. Right, everything would go through. There'd be no problem with anything. We turned everything around, and that's fine. Okay, what's the test statistic? Test statistic. Okay, there it is in symbols, and let me just plug in. So we have P2 is 21 women liked it out of 48 minus P2 hat, and P1 hat is 32 men out of 45 liked it, divided by the square root of, okay, well, we don't have P hat yet, P bar. P bar is, remember what it is? We add the successes up. It's 32 plus 21, 32 plus 21, and we divide by the sum of the total in each sample, which is 45 plus 48. So we end up with 53 over 93. So what is Q bar? It's 1 minus that. And you can see it's going to be, 93 over 93 minus 53 over 93 is 40 over 93. So I'm going to have P bar times Q bar, which is 53 over 93 times 40 over 93. And all of that divided by N1, sample size 1, which was 45, plus the same numerator, 53 over 93 times 40 over 93. all divided by this time, the second sample size was 48. Now, look, you know, you have to be sure. You should plug this in your calculator, make sure you can get the right calculations because, you know, there's a lot going on here. So I'm not going to run through the calculations. I'm just going to say that if you work it all out, you get negative 2.66 dot, dot, dot. All right, so what's the p-value? I'm going to have to switch here. Remember, it's a z-random variable. So here is negative 2.66. That's our test statistic, right? I look up that area, and I get 0.0039, right? Which is pretty low. It's pretty small here. So let me give the conclusion. I got to rub this out here so we have room for the conclusion. Because I think I have it on a slide, and I think it pretty much fills the board here. So that is a pretty small p-value. All right, it's less than 1%. So even at the 1% significance level, even at the 0.5% significance level, we would be rejecting the null, right? We would be rejecting the null. So I think we're going to reject the null here. So what do I say? I say our conclusion is, with a p-value of well under 1%, we conclude that there is sufficient evidence to reject the claim that the bombs are preferred by the same percentage of women as men, the same fraction or proportion of women as men. It appears men are more likely to prefer them than women. And that's it. So a greater proportion of men, it looks like, prefer them, which is another way of saying if you were to take a man at random, he's more likely to prefer chocolate-covered cherry bombs than if you were to just ask a random woman whether she did. All right, we'll stop there.